we're just finishing up the last little bit of energy. Specifically, we're talking about heat. Heat is a type of kinetic energy. Specifically, it's kinetic energy, and it's at the molecular level, hence why it's called the kinetic molecular theory. So if you recall, kinetic energy is the energy associated with motion, and heat is the motion of subatomic particles in place. So not to be confused with bulk kinetic energy, which is related to translation. And what that means is when one object moves from position A to position B. So that is what bulk kinetic energy is. Heat has to do with the vibration of the atoms or molecules themselves. So imagine a water molecule. Well, the heat is defined by the vibrations that occur in this direction, and the whole atom molecule itself vibrating back and forth. So the hotter something is, the more violent these vibrations are at the subatomic level. So the kinetic molecular theory helps to explain some observable phenomena such as pressure, heat conduction, convection, and radiation. So let's talk about pressure first of all. Well, let's give an analogy of something that you might be familiar with. Consider something like a 2-liter bottle of pop, or soda if you prefer. When it's in the fridge, it's quite cold, and then when you take that, especially if it's a brand new bottle, it's easy to squeeze the bottle itself. However, that same 2-liter bottle of pop, if you were to leave it in your trunk on a hot July day for a couple of hours, and then you took it out, unless you want a tsunami of soda everywhere, it's not recommended that you open up the bottle quite yet. And if you feel the container, it is rock hard. And the reason why that is because of the increase in pressure. So how is pressure related to heat? Well, essentially, these atoms are vibrating so strongly that they have these increased velocities. And then, of course, it requires more force to change the motion of each of these particles. So let's take a look at what I got over here in this particular example. So down here, we have 2 containers. Our first container, we have cooler material. The second container, hotter. So let's say these could be liquids or they could be gases. So the blue is to indicate a slightly lower temperature, which means that the velocities that they have are going to be significantly lower. So with the lower velocity, we get an action-reaction force. So when this collides, it's producing a force against the wall. Same over here. When we have a collision, another action-reaction force happens here. Action-reaction, action-reaction. So every time there's a collision with the wall of the container, we get these Newton's third law forces. Well, of course, there are trillions of these collisions. So we end up getting a uniform distribution of these collision forces on the container. So these forces cumulatively represent the pressure. Well, when the temperature increases, the velocities of these particular molecules increase dramatically as well. So when they smash into the container, the action-reaction forces are much more violent. So as a result, we have many more of these more violent collisions, and this represents higher pressures on the container itself. So as the temperature goes up, these collisions increase dramatically, which then brings us to the next idea, the concept of conduction. Well, what is conduction? So this is a form of heat transfer that is experienced mostly by solids, and the heat is transferred from one point to another via successive collisions between adjacent particles. So it's kind of like a domino effect. As each domino hits another domino, that energy is transferred each time. So I always give this the nickname as the mosh pit of chemistry. So basically what occurs is when one atom vibrates back and forth, it causes its next door neighbor to vibrate back and forth violently. And this continues on all the way down the line. So the energy transfer is in this direction. Now, if you notice the way that I drew it, there is a bit of a temperature gradient here, because as the heat transfers here, it's not 100% efficient transfer, because some of that heat radiates away into the environment. So some of that energy escapes here. So there's less energy traveling down. So this is still warmer, but it's obviously not as hot as here. So how does this occur? How do they actually interact in this manner when the atoms themselves actually don't touch? Well, again, it has to do with those invisible force fields. So let's do a little reminder. Atoms have positive centers, right? So you have your protons and you got your neutrons in the nucleus. And of course, surrounding that, we have our swarm of electrons. Proton, neutron, electron. So the outer shell, this outer shell is negative, and this outer shell is negative too. So we end up getting a natural force of repulsion between them. So if this atom moves in this direction, they get closer, which increases the action-reaction force. So if this atom moves over here, these two things get closer, this force increases, causing this one to move in this direction. And like dominoes, that effect keeps moving down the line. Now, of course, when this one recoils like this one feels this vacuum here of forces because we have a high area of pressure over here, and then it comes back and forth. So we get these sympathetic vibrations, and this is kind of similar to the way sound travels down the line as a result of these cascading Newton's third law force interactions between individual particles themselves. So that's how conduction works. As these atoms vibrate back and forth violently, the next door neighbors are induced to vibrate because it feels the force field of the electrostatic force. And the faster these things and the more rigorous they're moving, the more energy that gets transferred down the line. So the next concept is convection. So what is convection? Well, convection is a form of heat transfer that's specific to gases and liquids. It does not apply to solids because solids, the atoms themselves are not free to move. Only the electrons are allowed to move. And that's, I forgot to mention that in conduction, the main mechanism is the flow of these electrons. So it's the outer electrons. So we get the internal vibration, but then of course, electrons are also free to move. So you get electron flow. So the electrons interacting with other electrons that are free. So you get the atoms vibrating. You also get the freed ionized electrons vibrating, and the electrons do travel down these things. Now, the interesting thing is the key word is conduction, and another word that has the same root is conductor, right? So conductors actually have the highest level of conduction. So metal conducts heat as well as electricity very well. That's not a coincidence. That is, in fact, a feature. So now with convection, the actual entire atoms, molecules themselves move. So heat is transferred by the movement of the liquid itself, or the fluid, I should say. The fluid is just a general term because it applies to both liquids and gases. So as the heat source warms the surrounding fluid, we get an increase in kinetic energy. And that's the key, increase in kinetic energy of the particles, which causes the fluid to expand, thus decreasing the density. And of course, the less dense heated fluid rises as a result of the pressure generated by below. Now, this concept here, I need to explain a few things, a few big ideas. All right, so the question is, why is it that when we heat a source, why is the flow in this direction here? Why is it moving up? And because if the pressure increases here, the pressure is uniform in every direction. So why is it that the flow is favored in the upward direction? Well, again, it actually has to do with the nature of how pressure operates in a fluid. So let's consider this idea. Imagine the atmosphere or a body of water being a series of solid blocks. All right. So imagine we have a solid block like this, and we place the solid block on top of a scale. So it's a little spring scale here. Now, the weight of this block is going to push the spring scale down like this. Well, if I add another block on top, you should see that the scale is going to experience more force downward. And if I keep adding layers, the more layers I have, the greater the amount of compression I'm going to get down here. So we would expect that the scale would get crushed as we increase the number of layers. So what does the scale feel? Well, right now the scale feels a total of 1, 2, 3, 4, 5. A total of 5 of these rectangular blocks. All right. So if we were to imagine that each block, say, weighed 100 newtons, the total force that the scale would feel would be 1, 2, 3, 4, 500 newtons. All right. Well, what happens if we move up? Well, if we have a little pressure sensor here, it is only feeling the weight of the above 4. So this area here would only say feel 400 newtons. And then if I put the pressure sensor over here, 300, 200, 100, etc. So as you go higher, the amount of downward force from the weight of these rectangular boxes decreases. Literally, the exact same thing happens in our atmosphere. But instead of being a discrete rectangular container, they're just altitudes. And as you go higher, as your altitude increases, the total amount of air above your head decreases. And as a result, the downward pressure and the side pressure is also decreased. As we go up, the pressure is less. Well, if we take a look over here to the side, so if we overlay this sort of pattern here, the pressure at the very bottom from the atmosphere is going to be the highest. And as we move up, it's going to be the lowest. So what we've got is the outward pressure generated by the fire is going to is fighting against a level 5 pressure versus a level 4 versus a level 3 versus a 2 and versus a 1. So at this point here, directly above has the least amount of resistance pressure from the environment. So gases take the path of least resistance. There's too much atmospheric pressure down here to flow in that direction. So the tendency is you go where it's easiest. So the gases simply flow up like this. Now, as they flow up, they start losing some of their heat. And as they start losing some of their heat, they become more dense. And when they become more dense, then they become heavier per unit volume than the surrounding area. And as a result, those fluids then start to sink back down again. And then we get this convective cycle. And that's how the convection works. As this heat is generated, we have a flow going up like this. And of course, when we have material flowing in this direction, we have a vacancy, which gets filled in with the sinking material. And then we have this continual cycle of energy transfer. And this accounts for the winds in our atmosphere and the oceanic currents. And finally, the last way that heat is transferred from one position to another is the concept of radiation. Now, if you take a look at the root word of radiation, right, it's radii, right? And that's where we get radio, radiator, radius, radiation. So this implies that the energy is moving along radial lines. And if you think about it, when you're a little kid and you're sketching a picture of the sun, every little kid knows that when you draw the sun, it's like this. And then you have these things. And of course, it has to have a smiley face. Well, sometimes kids, you also will draw it like this. There's another image of a sun. All right. Well, it's funny that even as little kids, you actually are unconsciously representing the radiation component of the sun itself. And these are lines of radiant energy coming from the sun. And in what forms does it come from the sun? Well, we of course have the visible spectrum. We also have infrared, which is how the vast majority of the heat to our planet, that's how we get it, is in the form of infrared radiation, which is just below visible red. And this is the energy of heat. If you've ever been to a bonfire or turn on your stove and you put your hand just above the heater, please don't touch the heater. You can actually feel the heat coming off of it. If you've ever gone for a walk on a cool fall day or a cool spring day and the sun comes out, then all of a sudden within seconds, you're uncomfortably warm and you have to take off your heavier jacket. As soon as the sun goes away, you're freezing cold. And that has everything to do with the fact that the infrared radiation is either present or being blocked by the clouds. And of course, so we have infrared, we have visible, and there's also UV, which stands for ultraviolet. And these ones don't make it to the surface of the earth very much, but we also get X-ray from the sun, which these are very dangerous. And the most dangerous of them all is gamma ray radiation. So we are protected largely by our very relatively thick atmosphere, protects us from these things. And also we have many of the particles, the high energy particles, are deflected by our magnetic field. But in terms of the radiation, this stuff here is absorbed in the upper atmosphere. So again, radiation is the only form of heat transfer that does not require direct contact with the particles. And this is the only form of heat transfer that can travel through the vacuum of space. So the energy from the sun comes in this form, and this form is known as our electromagnetic waves. So electromagnetic waves are anything in the radio spectrum, infrared, visible, ultraviolet, that sort of thing. And these are a form of energy that is sent by particle-like objects called photons. And hopefully in grade 12, we'll talk a little bit about quantum mechanics and we get into some more of that. So your cell phone operates on microwaves. Same stuff that cooks your food is what sends memes across the internet. And the energy that we absorb, the heat received from the sun by the earth, we can only actually get rid of that energy in the form of electromagnetic radiation as well. And that is the cooling of the earth. So the earth, as it cools, it gives off infrared radiation. And that's where the whole global warming issue comes into play, is that we're actually putting gases in our atmosphere that is actually starting to inhibit the Earth's ability to cool itself off. So basically, we're putting a parka on the Earth during the springtime. Eventually it becomes summer. So now, the reason that this occurs, where we get these electromagnetic bits of radiation being produced, has to do with some quantum mechanical properties, which, it's kind of a little bit beyond the scope of this course. But essentially, weird stuff happens. When we talk about how atoms vibrate, their vibration actually can produce these forms of electromagnetic radiation based on the way the electrons get excited, jump from one valence shell to another, or the way the atoms themselves vibrate. So when we look at an atom, like, for example, a water molecule, we traditionally kind of draw it like this, so there's your two H's and there's your O, and we have like this little stick to represent the bond. But a better way to actually represent it is if we replace the bonds with springs, because what that implies is that we're going to get vibration in this direction, vibration in this direction, back and forth. We also get vibrations back and forth like this, and we also get vibrations back and forth like that, right? Where these get closer and further away. So all of these internal vibrations can get converted into other forms of energy, specifically radiant energy. So when these atoms collide with each other, right, you get very violent vibration. And these internal vibrations, the energy of these vibrations are eventually radiated away in the form of electromagnetic radiation. Specifically, most common is infrared radiation. That's why when an object gets hot, when you heat up an object with a heat source, we can see it glowing red. And before it glows red, you can actually feel that heat. And that feeling of heat that you feel is infrared. Infrared is invisible to us, but we can feel it through our temperature sensors on our body. And so that's basically the three ways in which heat is transferred. We have conduction, convection, and radiation. And of course, without radiation, the Earth would be a very, very cold place and lifeless. So the radiation is actually very important. So not all radiation is bad. In fact, radiation is quite necessary. So now let's talk about how to actually do some calculations with it. So there are some formulas. So when we talk about heat, we're talking about a form of kinetic energy. And this has to do, again, with the internal vibrations of the atoms and the molecules within a substance itself. So before we can actually discuss any of this stuff, we have to talk about something called the specific heat. All right. So this concept, it is the measurement of the amount of energy required to raise a certain mass of a substance by 1 degree Celsius. So kind of think of it as heat inertia. So all materials have different rates of heating and cooling. And those rates of heating and cooling have everything to do with the object's ability to absorb and hold thermal energy. So we can take, for example, let's consider a common experience in the summer here. You get into a very, very hot car. And I remember when I was a kid, seat belts were often made out of metal, which was an awful, awful material. Well, the internal parts, obviously metal because they're strong, but the outside, the actual of the mechanism was also metal. And in the hot July sun, those things would get so hot that you could actually burn your skin. Yet the bottle of water that is inside your car is still quite tepid. And that has to do with the heat absorbing capacity of the two materials. Steel has, or most metals, have relatively low specific heats. It takes very little energy for their temperature to rise up. where water has a very high specific heat, which means it takes a lot of energy to change its temperature. So we'll get into some examples, but before we do so, let's talk a little bit about what this idea of specific heat is. All right, so in physics, it is measured using joules and kilograms, which is different than in chemistry, because in chemistry, we use the gram as the standard unit. So for example, let's talk about water, because that's a very common substance, and it's one of the more important ones here. Water has a specific heat of 4.18 times 10 to the 3 joules per kilogram degrees Celsius. Okay, what does that mean? It means water requires approximately 4,180 joules of energy to increase 1 kilogram of water by 1 degree Celsius, So if we want to raise it by 2 degrees, we have to double that amount. If we want to raise it by 3 degrees, we have to triple that amount. Or if we double the mass, double that amount. If we triple the mass, triple that. So this is the amount required for just 1 single kilogram and to change it by 1 degree Celsius. Now, if you compare that with something like iron, if my memory serves me correctly, is about 820 joules. So iron takes a lot less energy to change its temperature by 1 degree Celsius. That is why in the hot sun, water will still stay relatively comfortable, but a piece of metal gets scorching hot because metals themselves require relatively little energy input to change their temperature significantly. And another example is the beaches in the summer. During the hottest part of the day, the sand is scorching hot, but the water itself is relatively cool. And if any of you have at one point made the same mistake that everybody makes at some point, in the excitement of getting to the beach, you start immediately running towards the water, but forget to put on your sandals. And of course, the sand is so scorching hot that your feet are on fire. So you're trying to, do this little dance of suffering until you get to the water. And then of course, the water is significantly cooler. However, if you go at night, it's a very different story. If you go at night, the sand actually feels quite cool on your feet. The sand is quite cool, but the water is relatively warm. So during the day, the water felt cool to you, but during the night, the water feels warm. Well, what gives? Actually, the water's temperature has remained fairly stable. It's just the temperature of the sand goes from extremely high to extremely cool during the evening hours. And that's because sand is basically crushed rock, and rock has a much lower specific heat, which means that it takes very little energy to heat up, but also, since it has a low specific heat, sand can't retain the heat for very long, and it dissipates it away quite rapidly, where water keeps the temperature stable. Okay, making connections times. This is why coastal cities tend to have very stable temperatures. Look at the climate of Vancouver. Vancouver doesn't get very cold during the winter, but it also doesn't, generally speaking, get super hot during the summer. The temperature range is more narrow. The entire island of Great Britain. So if you look at the Irish Isles and you look at all of the United Kingdom, or the British Isles, these places don't get very cold in the winter, but also don't get very hot in the summer. And that is because of the moderating effect of the Atlantic Ocean. The reason why people can actually live in places like Norway have entirely to do with the ocean keeping it unnaturally warm as a result of the Gulf Stream. And in the wintertime, even though Norway is at the same latitude as the Yukon, sometimes, in the city of Bergen, Norway specifically, which is a town that I've visited quite often, it rarely snows in the winter. It is quite tempered. But in the summer, the average temperatures generally stay in the high teens, low 20s, and very rarely do they ever get into the high 20s. Whereas Southern Ontario, our temperature ranges are fairly intense. It gets fairly cold in the winter and fairly hot in the summer, but nothing compares to the prairies, where the prairies go from extreme cold in the winter and extreme heat in the summer. The difference? The prairies are drier. Southern Ontario is more humid. Example number 10,005, deserts. The desert gets extremely hot during the day. 50 degrees Celsius is not uncommon for the desert. But at night, the temperature can drop as low as 12 degrees Celsius, sometimes even cooler. And that has to do with the fact that deserts have almost no water absorbed into the atmosphere, and the temperatures swing wildly. So areas that have low water content in the atmosphere, we have huge temperature ranges. So those are your drier areas, and areas that are surrounded or have lots of water content is the temperatures stay fairly stable. And everyone has experienced those lovely hot and humid nights in southern Ontario in July, where the temperature during the day is 32 degrees, and at 3 o'clock in the morning, it's still 31 degrees just without the sun. But if there was no humidity in there, the temperature would be a lot lower. All right, so now this number here again, this is a very important number to us. And this number, for those of you who are taking biology, might also recognize this as a calorie. So 1 calorie with a capital C is equal to 4,180 joules. Now, here's the little confusing thing. If you spell calorie with a small c, it's actually 4.180 joules. This is actually a kilocalorie, but for some reason, to make things confusing, we just put a capital C to make an indication of a kilocalorie. Don't ask me why that convention exists, but that's just the way that it is. So when you talk about your food calories, there's always this number thrown out, approximately 2,000 calories a day just to run the body. Okay, well, that's a gross generalization, right? So if you're like a larger athlete, physically larger, physically stronger, you need more than 2,000 calories. If you're a little kid, you need less than 2,000 calories a day. But that number is just often thrown out. Well, I want to point out that's 2,000 capital C calories. So you actually don't require 2,000 calories a day. You require 2 million small calories of food a day. Now that you might be saying, wow, that's a lot of energy. And it is. So why do we require so much energy just to survive, just to run our daily metabolic processes? Well, it has everything to do with water. The human body, is 70+% water, and it's at a temperature in the 30s, right? So our body temperature is about 36 degrees is the normal temperature. Well, the environment is significantly cooler than that. Your homes are generally set to, the low 20s. So that temperature differential between our comfortable environment and our body temperature means that the body constantly needs food to keep the core temperature at the appropriate temp, because we're constantly radiating that heat away. This also explains why there are some people who swear by training with less clothing during the wintertime, because the colder your body is, the more energy it has to burn. And if you're trying to lose weight, the idea is that if your body is cold, it's going to continually try to burn calories to keep you warmer. Your appetites tend to get a little higher in the winter months because you're constantly trying to replace that heat energy. My argument is it sucks being uncomfortable, so find other ways to lose weight. But so that's the big idea in terms of what a calorie is. Okay, so now here are the main formulas. So to calculate the change in thermal energy, we use the following formula. Now, we use a capital letter Q, and in chemistry, we use a little q. All this big Q means is the same as the change or delta heat, the change in heat energy. So instead of using delta EH, we use the letter Q. Not exactly sure why it was necessary to have a separate symbol for this instead of just using this. And I think largely it had to do with old typewriters where they didn't have the delta symbol. So using a capital letter was much easier when making textbooks before the advent of word processing software. So the Q represents the change in the heat energy in joules, right? So this little c represents that specific heat number. So I mentioned that for water, it's 4,180 joules per kilogram degree Celsius. Other materials have a different C. M represents the mass of the material in kilograms, and delta T represents the temperature change, in degrees Celsius. And I'm realizing here, I don't think I actually explained what M is, so I'm going to have to go back and re-edit my notes. I have a stupid way to remember this formula. I always call this country music delta television as country music television. Why? It's a stupid way, but I always remember that formula. CM delta T, country music delta television. If in case you're trying to remember a way of trying to remember it. Now, when we talk about heat transfer, this is again conservation of energy. And with this, the big idea is this: if let's say we throw a hot piece of metal in water. So when we throw a hot piece of metal in water, what's going to happen is following. The hot piece of metal is going to lose heat. And where is that loss of heat goes? That goes into the heat gain of the water. So again, if you recall, energy can't be created or destroyed. It can only be transferred from one form to another. So that basically means that heat transfers from one object to another. When does that heat transfer stop? The heat transfer stops when the temperature is the exact same. So that's the key. So heat transfer ends when the final temperature is the same of both materials, which brings me to my next point. Heat versus temperature. They are related, but they are not the same thing. Heat represents the amount of thermal energy in a substance. The temperature represents a measure of how fast the molecules are vibrating back and forth. They are related, but they don't mean the same thing. So let me give you an example. A cup of tea can be 100 degrees Celsius, right? So a cup of tea is 100 degrees Celsius when it first comes out of the teapot. That's very hot. So that has a high temperature. Well, let's say a swimming pool has a temperature of 18 degrees Celsius. All right. So this is your tea and this is your pool. Okay. So now definitely this higher temperature, lower temperature. The question is, what has more thermal energy, the cup of tea or the pool? And the answer is the pool. The pool has much more thermal energy than this cup of tea. And you might be asking yourself, well, why? Well, it actually has to do with the amount of mass. A cup of tea is a small amount, right? Has very little mass, whereas an entire pool is much larger. So to give you an idea of how to think about this, imagine I want to make an entire block of ice melt. All right, so we have this massive block of ice, okay? So the block of ice has a temperature of 0 degrees Celsius. So then you have this little tiny cup of tea. There's your little handle. Now, if you pour this cup of tea, right, boiling cup of tea onto our block of ice, sure, there's going to be some local melting here, right? And then we get a little bit of liquid water, but we will run out of tea before we significantly are able to melt this block. Yeah, locally, we are going to get some melting. And at this local area, we're going to get a lot of water produced, but the rest of the block is going to stay solid. But if you take this block of ice and you throw it into a swimming pool, this block of ice is going to melt. The whole thing is going to melt in this pool because the pool has a huge volume of water, which means that it holds a huge volume of heat. Because remember, the specific heat, this is measured per kilogram. So an entire swimming pool has an enormous number of kilograms of mass, which means that the total energy is going to be a multiple of the number of kilograms. So in order to change a pool, so let's say your pool is 10,000 liters. 10,000 liters is equal to 10,000 kilograms of water, right? So you need to multiply this number by 10,000. And that is how much energy is required to change the pool temperature by 1 degree Celsius. So that's why it takes such a long time to heat up your pool in the summer, is because it takes a huge amount of energy in order to do that. So it's not just about the temperature, it's also about the amount of stuff. All right, so let's take a look at some examples here. How much energy is required to raise 375 grams of gold by 13 degrees Celsius? All right, so first of all, we have to convert the grams into kilograms. And our change in temperature, our delta T, is positive 13 degrees Celsius. Now, where do we get this specific heat number? Well, we get that over here, right? On this table over here. So these numbers would be given to you on a table. So what this is, gold only takes 130 joules of energy to change 1 kilogram of its material by 1 degree Celsius. So again, compare that to water. Water is 4,180 joules. This is only 130. So what's the difference in there? Well, the amount of heat required to raise 1 kilogram of water by 1 degree Celsius could raise 1 kilogram of gold by 32 degrees Celsius. So the same amount of energy, right, would require water to only go up 1 degree. This would gain 32 degrees. Or the other way to look at it, it takes 1 kilogram of water, the same amount of energy to increase in temperature by 1 degree Celsius as 32 kilograms of gold does. So gold has a very low specific heat. So a little bit of heat energy changes this temperature quite radically. All right. So it's simply specific heat times the mass times the change in temperature. So that's only 603.3 joules of energy. Let's take a look at the next question. We're going to determine the temperature change of 7.5 kilograms of concrete if 4,542 joules of thermal energy is lost. All right, so the Q, the loss in energy, has to be a negative amount. So then, using the formula, Q is equal to Cm delta T. Isolating for delta T is going to be Q over Cm, and that works out to negative 0.2077 degrees Celsius. So as you can see, concrete has significantly more thermal energy capacity than gold does. So concrete is more in line with what water is, but still, water is almost double the amount of heat capacity as concrete has. And that again explains why cities get hotter in the summer, because concrete is not as much of a thermal sponge as water is. So that's why we have these things called urban heat islands, because we have less water in the city, more concrete, and therefore the temperatures do go up. All right, so now, next question. We have a 200 watt kettle, and it takes 4 minutes to come to a boil. Now, I hope you all realize that water boils at 100 degrees Celsius. Some people don't know that. I feel that you should. So if the initial temperature of the water was 14 degrees Celsius, how much water was in the kettle? All right, so first of all, time has to be into seconds. So 4 minutes is 420 seconds. Power is 200 watts. The initial temperature, the T1, is 14 degrees, and the final temperature, T2, is 100 degrees Celsius. And the specific heat of water is 4.18 times 10 to the 3. So first of all, we have to figure out the amount of thermal energy that was transferred to the kettle. So power is equal to the change in energy or work over time. So the amount of electrical energy that gets converted is going to be equal to the power of the kettle times the time. So 48,000 joules of thermal energy is theoretically transferred to the water. That's actually a bit of a lie, because some of that energy is going to go off into the environment. So it's not a perfectly closed system, but we're in physics law land here. So we'll just assume that the kettle is 100% efficient, which it is not. And all the water goes to heating up, all the energy goes to heating up the water. So again, this Q is the same as the change in the electrical energy. Now, technically speaking, here's what's occurring. This electrical energy is being converted into thermal energy. So technically, we're losing electrical energy and gaining heat. So that's why, you have electrical bill. You use up electrical energy and you produce energy in other forms. So isolating for the mass, we get the change in energy divided by C delta T, substituting in, and this kettle is a very low-powered kettle, because that is only 133.5 grams of water, and that took 4 minutes. So this is a pretty terrible kettle. Most kettles, I think, are closer to 1,000 watts, maybe even a little closer to 1,200 watts. And the reason why they can't get much higher is because in most standard homes in North America, the circuit limit for most circuits is about 1,800 watts. And that's why if you have too many appliances on in the kitchen at the same time, you'll flip a breaker. Okay, so the next one, this is conservation of energy big time. And as you can see, there's quite a bit of delicious algebra going on down here. So with this question is, we have a 200 gram chunk of iron, and it's heated to 175 degrees Celsius. And we place it in a bucket of water that contains 1 liter of water. All right. Now this water is initially at 15 degrees Celsius. So if no heat is lost to the environment, that's what I meant. No heat is lost. It means no heat is transferred to the environment. We want to find the final temperature of the water and the iron. Okay. Now here is the big idea. Heat transfer stops when the final temperature of the water is equal to the final temperature of the iron. That's the big idea here. So they are both going to reach the same temperature at some point. So when we look at the notation, I stands for iron. So that's the mass of the iron. The volume, V stands for the volume of water, which is 1 liter. Now, here's the important thing, even though I don't think I stated it here, is that 1 liter, oh, I did state it right here, that 1 liter has a mass of 1 kilogram. So the mass of the water is actually 1 kilogram. Now, the initial temperature of the water is 15 degrees Celsius. And the initial temperature of the iron is 175 degrees Celsius. So Ci stands for the specific heat of iron, which is 460. And actually, I think I got that wrong when I talked about it earlier. I said 800. Actually, iron's even less. It's 460. And water is 4,180. So water is almost 10 times more heat capacity as iron has. This explains why water is used as a coolant, because it's really, really some of the best that we've got. Okay, so now here's the big idea. What we know here is when we have a temperature exchange, a heat exchange, the loss of one equals the gain of the other. The alternate notation for this is the negative Q of A is equal to the positive Q of B, right? So Q is just the same as delta EH, right? So these questions require the most amount of algebra. So let's take a look at the notation, what's going on over here, and hopefully we can get this all clarified for you. So first of all, this states that the loss of heat of the iron equals the gain in the heat of the water, all right? So we have negative mass iron, specific heat of iron, times the change in temperature of the iron. But here's the thing. The final temperature of the iron is the same as the final temperature of the water. All right, so we got negative MiCi times the change in temperature of the iron is equal to the positive the positive value of the mass of the water times the specific heat of the water times the change in temperature of the water. So this is, again, this formula here is just Q is equal to Cm delta T. I just changed the orders of the M and the C, but that's not a big deal. All right, so now here's the thing is what we're trying to do is, and TF stands for the final temperature, right? So again, remember the iron's final temperature and the water's final temperature are the same. So what we're ultimately trying to do is we're isolating for these two terms. Well, the problem is they're both stuck in a bracket. So in order to solve this problem, we need to use distributive property to cancel out these brackets. So I am taking this and I'm distributing it across these two terms. Same with this, using distributive property. So that's where we get these intense terms. So what I'm going to do is this term here and this term here, we're going to have to bring to the same side of the equation. So where am I going to bring it? Well, this negative sign versus this positive sign. So my instinct, of course, is I'm going to take this term and I'm going to bring it to the other side. And at the same time, I'm going to take this negative term and bring it to this side here. So when I do that, this negative becomes a positive and this negative becomes a positive. So the next thing is I want to isolate for these two terms. These two factors. As you can see on the right-hand side, TF is associated with both of these terms. So I'm going to take a common factor of TF. When I take a common factor of TF, I get MWCW plus MICI combined. Next step is I'm going to take this entire factor and I'm going to divide both sides by it. So I end up getting this rather intense algebraic expression. And this is these are the most challenging of the questions here. So when we substitute the values in and we go through all the math, we end up getting a final temperature of 18.45 degrees Celsius. And this is both the final temperature of the iron and the water.